The morning of March 3rd, 1943. Above the Bismarck Sea, between New Guinea and New Britain, Captain Edward Larner pushed the control yoke of his B-25 Mitchell forward, dropping below 200 feet. The waves blurred beneath him. Salt spray misted his windscreen. This was not how medium bombers were supposed to operate. Then he pressed the trigger. 8 Browning AN M2 50-caliber machine guns erupted simultaneously from his aircraft's nose. The combined roar was unlike anything in aviation warfare. 6,400 rounds per minute of armor-piercing incendiary ammunition raked across the Japanese destroyer Asagumo at point-blank range. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The ship's superstructure disintegrated. Tracers ignited fuel lines. Secondary explosions rippled down her length. Within 90 seconds, the destroyer was dead in the water. This was not standard Army Air Force doctrine. This was innovation born from desperation, implemented through violation of regulations, and vindicated through devastating effectiveness. The man responsible had never attended engineering school. He held no advanced degree in aeronautics. He was a 43-year-old former Navy enlisted man who had talked his way into an Army commission. His name was Paul Irvin Gunn. Everyone called him Pappy, and what he did to the B-25 Mitchell bomber would change the course of the Pacific War. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem was straightforward. By mid-1942, American forces in the Southwest Pacific faced a logistical nightmare. Japanese convoys moved troops and supplies with near impunity. American heavy bombers attacked from altitude and missed. American fighters lacked the range. American torpedo bombers approached slowly and died quickly. The B-25 Mitchell, North American Aviation's twin-engine medium bomber, represented the most capable platform available. But its armament configuration revealed a fundamental misunderstanding of Pacific warfare requirements. The standard B-25C carried one 30-caliber machine gun in the nose, fired by a bombardier lying prone in the glazed nose compartment. 2 50-caliber guns sat in a dorsal turret. A ventral turret, operated by periscope, extended from the belly. Waist gunners manned additional 30-caliber weapons. This defensive arrangement assumed bombers would fly in formation at altitude, facing attacks from enemy fighters approaching from predictable vectors. It assumed bombardiers would have time to acquire targets through Norden bomb sites. It assumed warfare would follow pre-war doctrine. The Pacific Ocean cared nothing for doctrine. Japanese ships moved at night. They hugged coastlines. They dispersed before bombers arrived at altitude. High-level bombing achieved hit rates measured in single-digit percentages. The ventral turret proved worse than useless. Gunners became nauseated trying to track targets through the periscopic sight. The turret required nearly 1 minute to extend. In combat, 60 seconds meant the difference between life and death. Meanwhile, the 50-caliber Browning AN M2 sat unused in wrecked fighters across Australian airfields. Each gun weighed 61 pounds. Each fired at 750 to 850 rounds per minute. Each projectile carried enough kinetic energy to penetrate aircraft aluminum, ship plating, and human tissue with equal efficiency. The guns existed. The need existed. The connection did not. Enter Pappy Gunn. Born October 18, 1899, in Quitman, Arkansas, Paul Irvin Gunn was the son of a blacksmith. He learned mechanics, not through textbooks, but through necessity. When something broke on the farm, you fixed it. When tools didn't exist, you fabricated them. This practical, engineering education would prove more valuable than any university degree. In 1918, as World War I reached its final months, Gunn enlisted in the United States Navy. He served as an aviation mechanist's mate. He maintained aircraft. He understood how things worked, and, more importantly, why they failed. After the war, he learned to fly, purchased surplus aircraft, and parlayed his skills into civilian employment. By 1939, Gunn operated Philippine Airlines, flying passengers and cargo throughout the islands. He married Clara Louise Crosby. They had 4 children. Life was comfortable. Then December 7th, 1941 arrived. When Japanese forces invaded the Philippines, Gunn evacuated his family to Australia, or tried to. They were separated during the chaos. For months, Gunn believed them dead. They had, in fact, been captured and interned. This personal loss transformed technical competence into burning motivation. Pappy Gunn had reasons to fight beyond patriotism. The Army Air Corps, recognizing his aviation experience and mechanical expertise, commissioned him as a captain. At 42 years old, Gunn became one of the oldest junior officers in the Pacific Theatre. His age earned him the nickname Pappy. His skill earned him respect. His personality earned him latitude to bend regulations. General George Churchill Kenny took command of the 5th Air Force in July 1942. Kenny was himself unconventional, having advocated for tactical innovations the Army Air Corps establishment dismissed. He recognized in Gunn a kindred spirit. When Kenny observed Gunn installing additional 50-caliber guns into an A-20 Havoc light bomber at Townsville, Australia, he didn't reprimand the unauthorized modification. He promoted it. Kenny made Gunn his special projects officer. The assignment came with minimal written orders and maximum operational freedom. Translation: make our aircraft more lethal, and don't ask permission first. Gunn's initial experiments targeted the A-20. Removing the bombardier position created space in the nose. Stripping 50-caliber guns from wrecked P-40 fighters provided weapons. Fabricating mounting brackets required welding skills and improvisation. The result? An A-20 with multiple forward-firing 50s. The first combat test occurred September 12, 1942, against a Japanese airfield at Buna. The results exceeded expectations, but the A-20 had limitations: range, payload capacity, availability. The B-25 Mitchell offered solutions to all 3 problems. It could carry more bombs farther. More importantly, the 5th Air Force had them. Could the same modifications work on a larger airframe? Gunn moved to the 3rd Bomb Group at Charters Towers, Queensland. He requisitioned a war-weary B-25C. He gathered his team, technicians as unconventional as himself. They began cutting. The bombardier's compartment came out. The glazed nose panels were removed. Sheet metal fabrication created a solid nose. 4 50-caliber Browning AN Metu guns were mounted in a tight cluster. Ammunition feed systems were rerouted from the aircraft's existing supply points. Electrical firing circuits connected all 4 guns to a single trigger on the pilot's control wheel. Then, Gunn added more. Streamlined external pods were fabricated and mounted on each side of the fuselage, below the cockpit windows. Each pod contained 2 additional 50-caliber guns. This created structural challenges. The muzzle blast from 50-caliber weapons generates substantial force. Tests revealed the aluminum fuselage skin buckled under repeated firing. Gunn's team reinforced the affected areas with heavier gauge aluminum patches. Additional bracing connected the fuselage to the engine nacelles, preventing wing damage from recoil forces. The useless ventral turret was removed. Weight saved. Belly drag reduced. The dorsal turret remained, giving tail protection. Waist gun positions were relocated for better fields of fire. The final configuration mounted 8 forward-firing 50-caliber machine guns, 4 in the nose, 2 in each external pod, all controlled by the pilot, all firing simultaneously. The mathematics were straightforward. Each AN M2 fired approximately 800 rounds per minute. 8 guns multiplied by 800 rounds per minute equaled 6,400 rounds per minute, fired in a converging pattern at ranges of 300 to 500 yards. This created a cone of destruction unprecedented in medium bomber armament. But numbers on paper mean nothing without testing. The first test flight revealed immediate problems. The aircraft's center of gravity shifted dramatically forward with ammunition loaded in the nose. Standard takeoff procedures didn't work. The nose wheel wouldn't lift at normal rotation speed. Gunn's pilots adapted. They kept the nose wheel on the runway until reaching 120 miles per hour, instead of the standard 80 or 90. They increased turn speeds from 120 to 170 miles per hour. When technical officers at Wright Field learned of these modifications, they sent urgent messages. The alterations were dangerous. The center of gravity was outside acceptable parameters. The aircraft should be grounded immediately, pending engineering review. Gunn's reported response has entered military legend. Put center of gravity in storage for the duration. We have a war to fight. Whether those exact words were said or not, the sentiment was accurate. Regulations existed to prevent aircraft from crashing, but Japanese convoys were killing Allied soldiers. The modified B-25s killed Japanese convoys. The calculation was simple. Ammunition selection mattered as much as gun placement. The 50 caliber BMG, Browning machine gun cartridge, came in, multiple variants. Ball ammunition for general use, armor-piercing for hardened targets, incendiary for aircraft and fuel tanks, tracer for observation of fire. The Mate armor-piercing incendiary round, introduced in 1943, combined penetration with pyrotechnic effect. The 619-grain projectile left the muzzle at 2,910 feet per second. It could penetrate 3/4 of an inch of armor plate at 500 yards. Upon impact, the incendiary component ignited. The result, penetration followed by fire. By June 1944, the improved M20 armor-piercing incendiary round entered service. Better tracer compound, more reliable incendiary element. When 8 of these rounds converged on a target every 1/10 of a second, destruction was not a possibility but a certainty. The modified B-25s required new tactics. Skip bombing, developed by the 43rd Bomb Group's 63rd Squadron, provided the technique. Aircraft approached targets at extremely low altitude, below 150 feet. At 300 to 400 yards from the target, the pilot released bombs with delayed fuses, typically 4 to 5 seconds. The bombs skipped across the water like stones, striking the target at or below the waterline. The delay allowed the attacking aircraft to clear the blast radius before detonation. Combined with strafing, skip bombing became devastatingly effective. The 8 forward-firing 50s suppressed anti-aircraft positions and damaged superstructure. The bombs, delivered with minimal aiming error at point-blank range, destroyed the target's hull. Ships that survived the bombing burned from incendiary rounds. Ships that survived the fire sank from hull breaches. The Battle of the Bismarck Sea would prove the concept. March 2nd through 4th, 1943. A Japanese convoy attempted to reinforce Lae, New Guinea, with 7,000 troops aboard 8 transports, escorted by 8 destroyers. American intelligence detected the movement. 5th Air Force prepared to intercept. 13 B-17 heavy bombers struck first on March 2nd, achieving minimal results. High-altitude bombing against moving ships continued its dismal record, but the attack revealed the convoy's location and course. March 3rd brought Pappy Gunn's aircraft to the fight. 28 B-25 strafers, as they were now called, approached at wave-top height. A-20s and fighters provided cover. The strafers attacked in line-Aston formation, each aircraft selecting targets. The destroyer Asagumo became Captain Larner's focus. From 300 yards, 8 50s opened fire simultaneously. The sound was apocalyptic. The recoil forces rocked the aircraft. Tracers converged on the destroyer's bridge and forward superstructure. Steel plating designed to resist naval artillery shells was never intended to withstand this. Dozens of half-inch diameter projectiles, each moving at 3 times the speed of sound, each carrying incendiary compounds, struck per second. The bridge became an inferno. Fire control systems were destroyed. Anti-aircraft guns fell silent as their crews died. Secondary explosions rippled through the ship as ready ammunition ignited. Larner released his bombs. They skipped across the calm sea, struck the waterline, penetrated the hull, and detonated internally. The Asagumo listed immediately. Multiply this scenario across the convoy. Transport ships, lacking the armor of destroyers, disintegrated under concentrated fire. Oil tanks ruptured, ammunition stores exploded, troop compartments became death traps, Ships that survived the first pass faced second and third attacks as strafers returned, re-engaged, and departed only when ammunition was exhausted. By the battle's end, all 8 transports were sunk. 4 destroyers were sunk. Over 3,000 Japanese personnel died. American losses: 1 B-17, 3 P-38s, 2 B-25s. No American surface ships participated. The entire engagement was conducted by aircraft. The strafer B-25s were responsible for the majority of ship kills. Pappy Gunn's unauthorized field modification had achieved what sanctioned doctrine could not. The Pacific War's tactical calculus had shifted. North American aviation took notice. Factory representatives studied Gunn's modifications. Engineering analyses were conducted. The company incorporated elements into production models. The B-25G appeared with a 75mm cannon and additional machine guns. The B-25H carried 14 50-caliber guns. The B-25J, the most produced variant, was manufactured with either a glazed nose for conventional bombing or a solid nose with 8 50-caliber guns for strafing, plus 4 additional guns in fuselage packages. By 1944, the majority of B-25s in the place, Pacific Theater, were configured as strafers. They destroyed Japanese barges, moving troops and supplies along New Guinea's coast. They devastated airfields, catching aircraft on the ground. They sank hundreds of small craft. The psychological impact on Japanese forces was substantial. American air superiority was not merely quantitative, but qualitative. The success created new problems. Barrel life became critical. The AN M2's barrel was designed for aircraft use, with cooling provided by airflow at altitude. Low-level strafing generated sustained fire at low airspeeds. Barrels overheated. Accuracy degraded. Catastrophic failures occurred. Guns armourers developed quick-change barrel procedures, allowing replacement during turnaround maintenance. Synchronization of fire required careful adjustment. 8 guns firing simultaneously needed converging patterns. If convergence points were too close, the cone of fire was narrow but dense. If too far, the pattern was wide but diluted. Testing determined optimal convergence at 350 to 400 yards. At this distance, all 8 streams of fire intersected in a roughly 10-foot circle. Anything in that circle ceased to exist. Ammunition loading became an art. Belts were loaded with specific sequences. Every 5th round was a tracer, allowing pilots to observe their fire and adjust aim. The remaining rounds mixed armor-piercing and incendiary types. The tracers created a visible stream from aircraft to target, appearing as solid beams of light in combat footage. This was not Hollywood dramatization. At 800 rounds per minute per gun, the individual projectiles blurred into continuous streams. The weight of sustained fire affected aircraft handling. 8 guns firing simultaneously reduced airspeed through recoil. Pilots had to anticipate this. Approaching at 180 miles per hour, opening fire reduced speed to 160. This necessitated careful throttle management to avoid stalling during attack runs. The human element of operating these aircraft deserves emphasis. Piloting a strafer during an attack run required exceptional skill and nerve. The pilot approached at wavetop height, maintaining precise altitude while identifying targets, judging distance, timing weapon release, and executing evasive maneuvers immediately after attack, all while anti-aircraft fire converged on his aircraft. The din inside the cockpit during firing was physically painful. 8 50-caliber guns firing 2 feet from the pilot's position generated noise levels exceeding 140 decibels. Ear protection was mandatory. Even with protection, hearing damage was common. The vibration was intense. The muzzle blast created pressure waves that flexed the fuselage structure. Instrument panels rattled. Loose objects became projectiles. The smell was distinctive. 50-caliber guns fired nitrocellulose-based propellant. The combustion products, mixed with lubricants heated to vaporization temperatures, created an acrid smell that permeated the aircraft. Pilots and crew returned from missions with clothing saturated in gun smoke. The smell never fully washed out. Brass casings ejected from the guns accumulated inside the aircraft. Each gun ejected 800 empty cartridge cases per minute of firing. A 30-second burst generated 4,000 empty cases, each weighing approximately half an ounce. These cases, hot from firing, bounced around the crew compartment. Post-mission cleanup involved shoveling hundreds of pounds of brass from the aircraft's interior. Guns' experiments with the 75mm cannon generated publicity but proved tactically limited. The M4 cannon, adapted from the M3 tank gun, weighed 900 pounds without ammunition. It fired at approximately 1 round per 4 seconds. Recoil forces required substantial structural reinforcement. Accuracy from a moving aircraft at low altitude was marginal. Most significantly, the rate of fire was inadequate for suppressing targets. While a single well-placed 75mm shell could destroy a destroyer's fire control systems, hitting that target from 300 yards while traveling at 180 miles per hour was optimistic. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The 850 caliber guns, firing constantly, guaranteed hits. Guaranteed hits meant guaranteed destruction. Many B-25G and H models had their cannons removed in the field, replaced with additional 50 caliber guns. Gunn himself flew one such aircraft on combat missions. The official record credits him with the sinking of a Japanese destroyer using the 75mm cannon. Gunn's personal account was more modest. The cannon round damaged the fire control system. The subsequent bomb destroyed the ship. Supply logistics challenged every operation. The Southwest Pacific Theater faced chronic shortages of everything: 50 caliber, ammunition, spare barrels, replacement parts. Guns modified B-25s consumed ammunition at rates that terrified supply officers. A single strafing run expended 3,000 to 4,000 rounds, multiple runs per mission, multiple missions per day. The logistics were nightmarish. Gunn spent as much time scrounging as engineering. He flew throughout Australia and the Solomon Islands, visiting bases, inspecting wreckage, negotiating with supply officers. Any source of 50 caliber guns or ammunition became a target for Gunn's considerable persuasive abilities. His aircraft, a war-weary B-25 he named Out of Stock, became famous for its ironic designation. Whatever Gunn needed was always officially out of stock, yet Gunn always returned with it. The 4th Air Depot Group at Townsville became the primary modification center. Hundreds of B-25s cycled through, receiving strafer conversions. The work was systematic: remove, bombardier compartment, install, solid nose, mount 4 guns, fabricate and install external pods, mount additional 4 guns, remove ventral turret, reinforce fuselage skin, install ammunition feed systems, test fire on ground, test flight, combat mission, learn, modify. Repeat. The depot's efficiency improved through iteration. Early conversions required weeks. By mid-1943, conversions completed in days. Standard procedures emerged: templates for metal fabrication, jigs for mounting brackets, pre-measured reinforcement patches. What began as improvisation became systematized production. The psychological transformation of aircrew who flew strafers marked another cost. Traditional bomber doctrine emphasized altitude, formation, and mutual defense. Crew members trusted in numbers and distance. The strafer role eliminated both comforts. Pilots flew alone or in small formations. They engaged targets at ranges where enemy soldiers' faces were visible. They saw the immediate results of their actions. Yet voluntary transfer requests to strafer units exceeded available positions. The mathematics of survival played a role. Heavy bomber crews flying at altitude faced sustained anti-aircraft fire and fighter attacks throughout missions lasting hours. Casualty rates were substantial. Strafer missions, while intense, were brief. The approach was at low altitude, below effective anti-aircraft engagement envelopes. The attack lasted seconds. Departure was at maximum speed. The overall survival statistics favored strafer crews. Gunn's personal war intertwined with his innovations. In January 1943, he learned his family had survived and remained interned in the Philippines. This knowledge intensified his already substantial motivation. Every Japanese ship sunk meant fewer supplies reaching the Philippines. Every airfield destroyed meant reduced Japanese capability to hold the islands. Technical innovation became personal mission. He flew combat missions himself, technically prohibited for staff officers but tolerated given his special status. On these missions, Gunn tested new modifications under combat conditions. If something failed, he understood why before returning to base. If something succeeded, he understood the mechanism. This direct feedback loop accelerated development cycles beyond what formal engineering processes could achieve. The European theatre experimented with similar modifications but achieved less dramatic results. The tactical environment differed. German anti-aircraft capabilities exceeded Japanese systems. Heavily armed ships and concentrated flak positions made low-level attack prohibitively costly. The B-25s in Europe retained primarily their medium-altitude bombing role. Some Strafer variants operated against ground targets, particularly during the late war period when German fighter opposition declined. Pacific operations expanded the Strafer role continuously. The Philippines campaign, beginning in October 1944, saw extensive Strafer employment against Japanese positions. Iwo Jima and Okinawa operations included Strafer aircraft, suppressing defensive positions before amphibious landings. The cumulative effect was measurable. Japanese logistics networks were disrupted. Supply movements occurred only at night, reducing efficiency. Reinforcement attempts suffered heavy casualties. The Battle of the Bismarck Sea's strategic significance extended beyond immediate ship losses. It demonstrated that air power alone could interdict sea lanes without surface naval forces. This validated American air supremacy investments and influenced subsequent operations planning. The Japanese Navy's subsequent reluctance to commit large convoys in contested waters stemmed directly from Bismarck Sea losses. Papi Gunn never received the Medal of Honor his actions potentially warranted. He received the Distinguished Service Cross, Silver Star, Distinguished Flying Cross, and numerous other decorations. But the full scope of his contribution was obscured by classification requirements and the informal nature of his innovations. Official histories emphasized factory-produced variants while minimizing field modifications that technically violated specifications. In October 1944, during Japanese air raids on Leyte, Gunn was severely wounded. Shrapnel injuries ended his combat flying career. He was medically evacuated, eventually reuniting with his liberated family. His war service concluded with retirement as a lieutenant colonel in June 1948, with full disability benefits. Post-war, Gunn returned to civilian aviation, re-establishing his Philippine airline. On October 11, 1957, while flying a charter flight, his aircraft encountered severe weather. The crash killed all aboard. Papi Gunn was 57 years old. He was buried at Barrancas National Cemetery at Naval Air Station, Pensacola. His legacy persisted in the aircraft he modified. The B-25 Mitchell served into the 1950s with various air forces. The Strafer concept influenced subsequent close air support doctrine. The Aoni Sky Raider, designed in the late 1940s, incorporated lessons learned from Strafer operations: multiple forward-firing guns, heavy ordnance load, low-altitude operation. The lineage was direct. The unauthorized nature of Gunn's early modifications raised questions that persist in military innovation discussions. How much latitude should individual officers have to deviate from specifications? When does improvisation become reckless experimentation? Where is the line between initiative and insubordination? The answer, visible only in retrospect, depends on results. Gunn's modifications worked. They increased combat effectiveness. They reduced American casualties while increasing enemy losses. From this perspective, the regulatory violations were justified. But this creates precedent problems. Other unauthorized modifications failed catastrophically. Selection bias favors successful innovations while forgetting failed experiments. General Kenny's command philosophy enabled Gunn's success. Kenny valued results over procedures. He protected subordinates who produced results even when their methods violated regulations. This created an environment where innovation flourished, but it also created risks. Not every unconventional officer possessed guns competence. Kenny's challenge was distinguishing productive innovation from dangerous experimentation. The technical success of the strafer modifications obscures their operational costs. The increased forward armament came at the expense of defensive capability. Bombardier positions were eliminated, reducing precision bombing capacity. The aircraft became specialized tools, highly effective in specific roles but less versatile than standard configurations. Guns innovations also highlighted American material advantages. The modifications required abundant supplies of .50 caliber guns, unlimited ammunition, and mechanical expertise to install and maintain complex systems. Japanese forces, operating under severe resource constraints, could not have implemented equivalent modifications even had they conceived them. American industrial capacity enabled experimentation that resource-limited forces could not afford. The 8-gun strafer configuration represented optimal balance given existing technology. More guns would have exceeded structural limits. Fewer guns would have provided insufficient firepower density. The convergence of available weapons, airframe capacity, tactical requirements, and manufacturing capability produced a system whose components fitted together almost accidentally. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The impact extended beyond immediate, tactical victories. The strafer modifications influenced American aircraft design philosophy for decades. The concept of concentrated forward-firing armament became standard in subsequent attack aircraft development. The Aoni Skyraider, developed in the late 1940s, carried 4 20mm cannons in the wings. The Aton Thunderbolt, designed in the 1970s, mounted a 30mm 7-barrel Gatling gun. The doctrinal lineage traced directly to Pappy Guns field modifications in Australian hangars. The psychological effect on Japanese forces deserves examination. After Bismarck Sea, Japanese convoy operations changed fundamentally. Large-scale troop movements by sea became rare. Supply convoys travelled only at night. Ships dispersed rather than concentrating. The presence of American aircraft forced tactical adaptations that reduced Japanese logistical efficiency throughout the remaining war years. Japanese after-action reports, captured and translated post-war, described the strafer attacks in terms suggesting psychological trauma. The sound of multiple machine guns firing simultaneously, the visible tracer streams converging, the inability of return fire to stop attacking aircraft. These elements created terror beyond simple military effectiveness. Ships' crews who survived attacks often refused subsequent convoy duty. The modifications also affected American aircrew culture. Strafer pilots developed distinct identities within bomber commands. They painted elaborate nose art. They named their aircraft aggressively. They wore non-regulation flight gear. This reflected the specialized nature of their missions and the autonomy required for low-level attack operations. Command structure adapted, granting strafer units operational latitude unavailable to conventional bomber squadrons. Technical innovation continued throughout the war. Some B-25 strafers received experimental armament, including rockets mounted under wings. Others tested incendiary ammunition specifically designed to ignite aviation fuel in Japanese aircraft. Their strafer platform became a testbed for weapons development, with successful innovations spreading rapidly through theater-wide implementation. The maintenance challenges were substantial. 8 .50 caliber guns firing thousands of rounds per mission required constant attention. Barrels wore out, feed mechanisms jammed, firing solenoids failed. Each aircraft required dedicated armament specialists who understood the complex systems gun had installed. The 4th Air Depot Group trained maintenance personnel specifically for strafer aircraft, creating specialization within existing maintenance structures. Ammunition expenditure rates challenged supply chains at every level. A single strafer squadron conducting daily operations consumed more .50 caliber ammunition than an entire fighter group. Supply officers learned to prioritize strafer ammunition requests, recognizing that mission effectiveness depended absolutely on ammunition availability. Ships carrying ammunition to Pacific bases allocated cargo space specifically for 50 caliber supplies destined for strafer units. The convergence of tactical need, individual initiative, and command support created conditions where innovation flourished. Without Japanese convoy targets, the strafer modifications would have been unnecessary. Without guns' mechanical expertise, they would have been impossible. Without Kenny's protection, they would have been prohibited. All three elements aligned at precisely the moment required. This raises questions about military innovation processes. Formal research and development channels existed. Testing protocols were established. Approval procedures were documented. Yet the most effective tactical innovation in Pacific theater bomber operations emerged from unauthorized field modifications conducted by a single officer with minimal oversight. What does this reveal about institutional innovation capacity? The answer is uncomfortable. Large organizations optimize for reliability and safety, not rapid innovation. Review processes exist to prevent failures, but also slow implementation. In peacetime, this balance favors caution. In wartime, especially when losing, the calculation shifts. Kenny recognized this and created space for Gunn to experiment. The results justified the risk, but only because Gunn's competence matched his authority. Other officers attempted similar unauthorized modifications with disastrous results. Aircraft were damaged, crews were injured, resources were wasted. These failures disappeared from official histories while Gunn's successes were documented. Survivorship bias creates misleading narratives about innovation. We celebrate successful violations of procedure while forgetting unsuccessful ones. The strafer story also reveals tension between individual initiative and institutional authority. Military organizations require discipline and standardization. Operations cannot function if every officer modifies equipment according to personal preference. Yet rigid adherence to doctrine prevents adaptation to changing circumstances. The balance is delicate and context-dependent. Gunn's modifications succeeded because they addressed genuine tactical problems. High-altitude bombing wasn't working. Japanese convoys were succeeding. American casualties were mounting. The need was obvious and urgent. In this context, experimentation was justified even without formal approval. But this creates precedent that can be exploited by less competent officers facing less clear-cut situations. The post-war period saw attempts to formalize the lessons learned. Technical manuals documented strafer modifications. Training programs incorporated low-level attack techniques. Aircraft designers included concentrated armament in new attack aircraft. The informal knowledge developed in Australian hangars became institutional doctrine implemented globally. Yet something was lost in formalization. The adaptability that characterized Gunn's approach became rigid procedure. The willingness to experiment became standardized process. Innovation that emerged from desperation became routine operation. This is the inevitable trajectory of successful adaptation, but it reduces the flexibility that enabled success initially. The broader historical significance extends beyond aviation. Gunn's story illustrates how technological advantage emerges not just from superior resources, but from superior implementation of existing resources. Japan possessed skilled pilots and capable aircraft, but Japanese military culture discouraged unauthorized modification. Doctrine was rigid, individual initiative was suppressed. This cultural difference translated into tactical disadvantage. American military culture, despite its emphasis on rank and regulation, maintained space for individual initiative. Officers like Gunn could propose ideas, test concepts, and implement solutions without lengthy approval processes. This cultural characteristic provided asymmetric advantage that complemented material superiority. The combination proved overwhelming. The human cost of strafer operations deserves acknowledgement. Low-level attack missions were brief, but intensely dangerous. Anti-aircraft fire at close range was lethal. Engine failure at wave-top altitude allowed no recovery time. Navigation errors over open ocean were fatal. The crews who flew these missions accepted risks that conventional bomber crews avoided through altitude. Casualty statistics for strafer units were complex. Per-mission casualties were lower than heavy bomber formations, but strafer crews flew more missions because each mission was shorter. Cumulative risk approached that of high-altitude operations while introducing different failure modes. The psychological stress was distinct. Altitude provided psychological distance from violence. Strafer crews witnessed destruction directly and personally. The veterans who survived carried memories that differed from conventional bomber crews. They described the smell of burning ships, the sight of sailors abandoning vessels, the sound of secondary explosions. This proximity to destruction's consequences affected some more than others. Post-war psychological effects were documented but not systematically studied. Papigun's legacy ultimately transcends technical innovation. He demonstrated that individual competence, given authority and resources, can transform operational effectiveness. He showed that institutional flexibility enables adaptation. He proved that tactical problems sometimes require unconventional solutions implemented rapidly rather than perfect solutions developed slowly. His story also reveals costs and risks. Not every unauthorized modification succeeds. Not every unconventional officer possesses necessary competence. The balance between innovation and discipline remains perpetually contested in military organizations. Gun's success provides justification for both sides of this argument. The B-25 strafer modifications changed Pacific War outcomes measurably. Japanese logistics were disrupted, Allied operations were supported, American casualties were reduced. These effects stemmed from one man's refusal to accept ineffective doctrine and his willingness to violate regulations in pursuit of tactical effectiveness. This brings us to the central irony. The unauthorized field modification that violated specifications and concerned engineers became the standard configuration incorporated into factory production. The improvisation became doctrine. The violation became policy. What started as one man bending rules to solve immediate tactical problems evolved into systematic implementation across an entire theater of operations, eventually influencing aircraft design philosophy for decades. In March 1943, above the Bismarck Sea, Captain Larner pressed his trigger, and 850 caliber machine guns destroyed a Japanese destroyer. That moment represented the culmination of months of unauthorized experimentation, the validation of one man's vision, and the beginning of tactical transformation. Papigun's modifications didn't just increase firepower, they changed how America fought the Pacific War. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.